Okay, welcome ladies and gentlemen to section 2 or lesson 2 from unit 5, looking at a very big theorem called the mean value theorem. This particular theorem shows up on free response questions for the AP test every once in a while, or quite often depending on who you talk to. So let's go ahead and take a look at what it looks like. There's a lot of stuff going on in this particular lesson, but the mean value theorem is one of the big ones here. So the mean value theorem states this: if you are given a continuous function on some closed interval that is also differentiable at every point on the interior, so that means like no cusps and no jumps and that sort of stuff, no holes, all that sort of extra stuff, but that's continuous as well, then there's at least one point on the function or on that interval in which you have a tangent parallel to the chord or secant line, depending on what word you want to use there. We've used secant quite often. So basically what that means, is it's almost an obvious statement, but it's a very important statement when it comes to AP calculus. If you have some continuous function that looks like this, in between A and B, the slope of this line, which is the chord or the secant line, is going to equal the slope of the tangent line for some value on that curve. So this being f of c right here. So we can look at this. We want to show that the function x squared satisfies the hypotheses of the mean value theorem on the interval from 0 to 2. If you were to say something about this, you would actually have to verify the first pieces. You would have to say x squared is continuous on 0 to 2, and it's differentiable on the interval from 0 to 2. That sets up the beginning of the theorem. We could then prove the rest of this, showing that this follows the MVT, saying let's find the slope. We want to find f prime of c that is going to equal f of 2 minus f of 0 all over 2 minus 0. So f of 2 is going to be 4. F of 0 is 0 over 2. So we get 4 minus 0 over 2, which is 2. So we want the derivative at some value equal to 2. Well, f prime of x is 2x. So we want 2x to equal 2, and it just so happens there is some value, and that value happens to be 1. That gets you the same slope as the slope of the chord from the two endpoints, 0 to 2. Okay, moving forward to some of the other little things we got going on here. Another one of those things that we start looking at is graphs, and we're going to compare graphs here after a while. First thing we need to know is we know a lot about increasing and decreasing portions of a graph. But we can actually extend that into calculus. From what we learned in the pre-calculus level, we can extend it to calculus by looking at the derivatives. If you have a continuous function that is differentiable on a to b, continuous on the closed interval, then if your derivative is positive, then the function is increasing. And that should make sense, because if the derivative is positive, that means the slope is positive, which means the original function is increasing. And you might remember we did this way back at the beginning when we started learning about derivatives. We looked a little bit at graphs. We can look at them a little bit deeper now coming up. Likewise, we can say the derivative is less than 0, then the function f is decreasing on that interval. All right. Basically, what you're going to be trying to do is find parts where a certain function is increasing or decreasing, technically without trying to use a calculator. You can find the derivative of the function and figure where that function is positive and where the function is negative, or where the derivative is positive or negative, and I'll tell you where the function is increasing and decreasing. Other things that happen. If the derivative is equal to 0, we should understand this. If derivative is 0, it's just a constant. So it's saying if your derivative is 0 at each point on some interval, then there's a constant c for which f of x equals c for all x in that interval. Basically, if your derivative is 0, you could have had f of x equal to 3. You could have had f of x equal to 7. Notice that both of these derivatives are still 0. You could have f of x is equal to negative 3. And this really gets into the next piece on this same page here. If you have two derivatives that are equal, there is a c value that shows that the original function f could be a constant, just a difference away from c, or from g of x. So if I was to give us the functions 2x plus 3 as f of x, and g of x is 2x minus 7, you notice that the derivatives are the same. But the original functions were not the same. The reason this comes in handy is because the next thing that we're going to be looking into is this idea of an antiderivative. That's actually my next page here as we continue going. The antiderivative is trying to figure out, if you were given a derivative, what could the function have been in the first place? You'll notice that f of x is 2x plus 3, but g of x is some distance away from 2x plus 3. It's actually minus 10 away, right? It's 10 units away from the original f of x. So here's what I mean. The antiderivative. The antiderivative is a function for which, if you took the derivative of it, you would get f of x. So what we're going to be doing here is this big long word called antidifferentiation. Basically saying, if I was to give you g prime of x is equal to 2, g of x, or let's use the, oh no, we were going to say g of x. We could say g of x could have been 2x plus some number. And you might recall this from one of my tests from previous in the class. Some of you guys wrote numbers out here, some of you guys didn't. But what we do in here is we write a big C, because we don't know what that constant is. It could be anything. Because the derivative of this function is 2, because the derivative of a constant is 0. So here's a question you might be asked. Whose function, or what is a function whose derivative is sine of x? Now we know the derivative of cosine of x is equal to negative sine, which means the derivative of negative cosine x is positive sine. So the antiderivative of sine x is negative cosine of x plus c. Now the problem is this is infinitely many answers because I could let c be any number. So what we do in calculus, we say we give you an initial condition. We say, well, it should pass through the point 0, 2. So we're giving us the function f of x is equal to negative cosine of x plus c, and it has to pass through the point 0, 2. So my y value is 2. What we need to figure out is what is the c value in this particular problem. You have to remember that the cosine of 0 is 1. Oops. Therefore, c is 3, which means we start off with saying, okay, what's the function whose derivative is sine of x? It's the cosine of negative cosine of x plus c. But if we want to find c, you have to have been given a point. Then you can find the c value, and therefore the actual antiderivative is negative cosine of x plus 3, and that's the actual antiderivative. If you have all of your derivative rules down, finding the antiderivatives does not come as too much of a challenge. And it will come in handy when we come into integration, which comes up in the next unit. So since I told you don't have an assignment sheet just yet, here is your assignment just out of the textbook. I will have all of that stuff ready for you guys tomorrow. Hope you learned a little bit, and I will see you guys tomorrow.